Hello everyone and welcome to part 2 of our lecture about Fermat's little theorem. In this one we will prove Fermat's claim, which is, let me remind you, if p is a prime number, then for every integer n to the p is congruent to n modulo p. We've seen in our previous lecture that Fermat was trying to factor numbers of the form 2 to the n minus 1 when n is a prime number. A straightforward way to do this is to successively divide it by all the primes up to its square root. But for instance, the square root of 2 powers 37 minus 1 is almost equal to 370,727, and the number of prime numbers lesser than this number is equal to 31,579. So checking this huge amount of prime numbers is a great amount of work if you're not lucky enough, and at least without any computer. Now instead of checking prime numbers divisors of 2 to the n minus 1, Fermat turned this differently and asked for a fixed prime number p, which power of 2 is congruent to 1 modulo p. Before we dive into more technical details, let us see what happens when p is equal to 17, which is, let me remind you, a prime number. 2 to the 0 is congruent to 1 modulo 17, and this is because 2 to the 0 is equal to 1. 2 powers 1 is congruent to 2 modulo 17. 2 powers 2 is congruent to 4 modulo 17. 2 cubed is congruent to 8 modulo 17. 2 powers 4 is congruent to 16 modulo 17. It is all obvious until here. 2 powers 5 is congruent to 32 modulo 17, and 32 is the same thing here as 15 modulo 17. Now what I'm looking for is the first power, not equal to 0 of course, for which 2 powers n is congruent to 1 modulo 17. Let me go further, and if I compute 2 powers 6, it is the same thing as 2 powers 5 times 2 modulo 17, and 2 powers 5 is 15 modulo 17 from here, so 15 times 2 is 30 modulo 17, which is the same thing as 13 modulo 17. Okay, I'll stop here because these are tedious computations, and I will ask Python to do them for me. I wrote for this purpose a little computer program that will do the job for me. Here, power LST is an empty list that my program will fill up with the powers of A modulo P, of course. So if I run this with power of 2 modulo 17, for instance, one gets 1, 2, 4, 8, 16, 15, 13, 9, and here we get the one that we're looking for. Let me remind you that this is exactly the same thing that we found here. Now I know that 2 power 6 is 13 modulo 17, 2 power 7 is 9 modulo 17, and 2 powers 8 is 1 modulo 17. So the smallest positive power of 2, which yields 1 modulo 17, is 8. Let us check now how things work for 3. So if you ask Python power of 3 modulo 17, one gets this list, and notice here that the first positive power of 3, which is congruent to 1 modulo 17, is the last one, which is 16 here. Let me remind you that I'm repeating these instructions p time, from 0 to p minus 1. So this is 16 when p is equal to 17. Thus, 3 powers 16 is congruent to 1 modulo 17, and 16 is the smallest power that gives us this result. Notice that 16 is p minus 1 and is the same thing as Fermat's little theorem, which states that 3 powers 17 minus 1 should be 1 modulo 17, which is the case here. Now if we try with 4, power of 4 modulo 17 still, this is what we get, and the first positive power of 4, which gives 1 modulo 17, is 4. So 4 to the 4 is congruent to 1 modulo 17. What we see next is actually once we get to 1 here, the remainders will be the same as the first remainders, so 1, 4, 16, 13, 1, 4, 16, 13, and so on and so forth. It is the same thing actually here too with power 2 and 17. We have a 1, 2, 4, 8, 16, 15, 13, 9, and 1, and then the same remainders until we get a 1 here. Now if you try this with another prime number, let's say power of 2 modulo 23, this is what we get. And notice the same thing, we get 1 here, and as soon as we get a 1, the remainders will be the same until we get another 1. I suggest you computer program this by yourself and check for another patterns that occur while computing the power of a number A modulo P. One more pattern to recognize here, which was used by Fermat to factorize 2 to the 37 minus 1, is to see that p minus 1 will always be a multiple of the first positive power of 2, which gives 1 modulo the prime number p. So we can see it here because this is 2 powers 8, and 8 divides 16, which is 17 minus 1, meaning p minus 1. Here the first positive power is p minus 1, which is divisible by p minus 1. Now here the first positive power of 4, which gives 1 modulo 17, is 4, and 4 divides 16. And in this example, p minus 1 is equal to 23 minus 1, which is 22. And if you count here, you will recognize that this is 2 powers 11. That gives 1 modulo 23. Actually, it is very easy to see why there is a power of a congruent to 1 modulo p each time. And this is because a to the n will give remainders modulo p. And since there are finitely many remainders, this means that for a certain integer m, we will have that a to the n is congruent to a to the m modulo p, which means that a to the n and a to the m will have the same remainder, because we have p minus 1 remainders, such that, of course, m is greater than n, in which case we get that a to the m minus n is congruent to 1 modulo p. So there will always be an integer for which a to the n is congruent to 1 modulo p, and if you call the smallest positive integer, verifying this condition d, which means a to the d is congruent to 1 modulo p, and that d is the smallest one, then d must divide p minus 1. It is actually easy to see because from Fermat's claim we have that a powers p minus 1 is congruent to 1 modulo p, when of course a is not congruent to 0 modulo p. So if you divide p minus 1 by d, one gets that p minus 1 is equal to d times a certain integer k plus a certain remainder r, which is strictly lesser than d. Now if you take a powers p minus 1, we get that it is equal to a powers dk plus r, which is the same thing as a powers d all powers k times a powers r, and this is congruent to 1 powers k times a powers r modulo p, which means that a powers r is also congruent to 1 modulo p, because a powers p minus 1 is congruent to 1 modulo p, so this is what we get, a powers r is congruent to 1 modulo p, which implies that r must be equal to 0. And you know why? Because d is the smallest positive integer for which a powers d is congruent to 1 modulo p. So this cannot hold because r is strictly lesser than d, which means that r must be equal to 0, and that here p minus 1 is equal to d times k, which means that p minus 1 is a multiple of d. Let us now move on to the proof, but first we're going to prove an interesting lemma, a pattern that happens modulo a clock of p hours when p is a prime number. And let me remind you that we would like to prove for an integer a that a to the p is congruent to a modulo p. What we would like to see here, if we fix an integer a, what happens when we multiply this a by 1 modulo p, then when we multiply it by 2 modulo p, then a times 3 modulo p, until we get to a times p minus 1 modulo p. For instance, if you take p equals to 7 and a equals to 5, then a times 1 is the same thing as 5 times 1, which is congruent to 5 modulo 7. A times 2 is the same thing as 5 times 2, which is congruent to 10 modulo 7, and this is 3 modulo 7. A times 3 is 5 times 3, and it is congruent to 1 modulo 7. A times 4 is 5 times 4, which is congruent to 6 modulo 7. A times 5 is the same thing as 5 times 5, which is congruent to 4 modulo 7. And a times 6 is the same thing as 30, which is congruent to 2 modulo 7. There is something very important to notice here, but before I tell you what to notice, let us do this on Python to see more examples. I wrote for this purpose a little computer program that I call here multiplication of a and p, and we would like to multiply a by I here, which ranges from 1 to p minus 1. So I have an empty list here that will be filled with a times I modulo p. Now if I run this and ask Python for multiplication of 5 and 7, and this is the same example I just investigated, one gets 5, 3, 1, 6, 4, and 2, and this is the same thing that we got here, 5, 3, 1, 6, 4, and 2. Now if you do this with more examples, let's take 6 and 19 as a prime number. This is what we get, and notice that all the numbers here are different modulo 19, and we get all of them from 1 until 18. And actually it is the same thing here, we get all of them from 1 until 6, which is p minus 1. Now if you do this with another example, say the multiplication of 10 modulo 13, this is what we get, 12 numbers modulo 13, and they're all different, which means we get all the hours on the 13 hours clock. Same thing here and same thing here. So notice here that we fixed an a and we multiply it by all the hours of our clock from 1 until p minus 1. Of course, I do not multiply it by 0 because we get a 0. And this is a rearrangement of our hours, which means that we will get all the hours on our clock, but in a different order. Now to prove this fact, all we have to do is to prove if I is greater than 0, lesser than j, which is lesser or equal to p minus 1, a times I cannot be congruent to a times j modulo p. And this means that we get all the hours on our clock when we multiply a by all the other hours. Indeed, if ai were congruent to aj modulo p, which means that they give the same hour, it implies that ai minus j is congruent to 0 modulo p, which means that p must divide a times a minus j. By the Gaussian lemma, this means that either p divides a or p divides a minus j. This cannot hold because a minus j is strictly lesser than p, and the only number that's strictly lesser than p that is divisible by p is 0, which means that I minus j must be equal to 0, or in other terms that I is equal to j. But of course this is wrong from our assumption here. This cannot hold because it would mean that a is congruent to 0 modulo p, and let me remind you that I took a strictly greater than 0 and lesser than p minus 1. Hence the desired result here. I claim that now we're ready to prove Fermat's little theorem, and let us take 1 times a times 2 times a times 3 times a times 4 times a until we get to p minus 1 times a. This is actually a rearrangement of all the elements modulo p, which means that we will get that this is congruent to 1 times 2 times 3 times 4 until we get to p minus 1 modulo p. So if we rearrange this, we put 1 with 2, with 3, with 4 until we get to p minus 1, and the a's together. Notice here that I have p minus 1 elements, so we get that 1 times 2 times 3 until p minus 1 times a to the p minus 1 is congruent to 1 times 2 times 3 until we get to p minus 1 modulo p. Of course, let me remind you here that I'm taking a not congruent to 0 modulo p, which means that a is not divisible by p. This number here to the left is the same number here to the right, which we denote p minus 1 factorials times a powers p minus 1 congruent to p minus 1 factorials modulo p. Now this implies that p minus 1 factorials times a to the p minus 1 is congruent to 0 modulo p, which means that p must divide all this number here, but p cannot divide p minus 1 factorial because p does not appear in its factorization here. So by the Gaussian lemma, p must divide this number here. Thus we get that a to the p minus 1 is congruent to 0 modulo p, which is the same thing as a to the p minus 1 is congruent to 1 modulo p, and this is Fermat's claim. What we got here is when a is not congruent to 0 modulo p, then a to the p minus 1 is congruent to 1 modulo p, and if you multiply both sides by a, one gets Fermat's last theorem that a to the p is congruent to a modulo p. Actually, this also holds when a is congruent to 0 modulo p because 0 to the p is also congruent to 0 modulo p. So this holds only when a is not congruent to 0 modulo p, but this holds even when a is congruent to 0 modulo p and for a not congruent to 0 modulo p. Our lecture about Fermat's little theorem ends here. and we will see how powerful it is in number theory and in cryptography in future lectures. Thank you for listening.